Hello everyone. Just wait for some time for others to join and then we can give it a start. Hi Rohit. I think we can give it a start. Uh, let Sarang join in as well. Give me 1 minute. I think this is the one. Yeah, so let me just rename this file as 24. This one as 24th of August. I hope you can see my screen, right?
Yes.
Yeah. So let's just see what we have done. Okay. Yeah. So let's just quickly write down a couple of lines of notes and then we can continue. So we have seen in the last class that we can convert the categorical variables, yeah, categorical variables with two or more than two classes of values into numerical variables using methods like label encoding and one hot encoding, but it is not necessary. It is not necessary that always such variables will add value to our regression analysis. Yeah. The second thing that we have noticed is that, give me 1 minute. Yeah. The second thing that we have noticed, if you remember over here, um, also p-value is a good indicator overall to the understand the, let's say, importance of each of the features, yeah, or independent variables used in the analysis, right? uh, but there are also cons of using p-value, which we will explore later. Yeah. So let's not go into the details of why there are certain cases where p-value is not good. uh, I can share you a link where when is p-value not a good measure, right? Somehow in our LMS, I'm not able to share these points, but there are certain things. I believe I can share such PDF files. Let me see if I can share such kind of documentation, because there are certain cases where p-value is not really a very good or let's say useful measure in case of the testing of significance, Okay, there are specific cases only. Otherwise, holistically, it is quite good. It is quite easy, and also it is quite relatable. I mean, if you use p values, you can relate to them quite easily, quite directly, and hence they can be used almost anywhere. I mean, there is no such restriction that in this domain or in this field only we can use it, and in the others we can't. Right. So that's the reason why overall p values are going to be very essential. Like we have seen over here, example given. In this case, we can clearly see what we can find out from the p-value, right? So significance of p-value is there, but not always, right? So when we progress with more and more use cases, we will come to know that there will be, let's say, scenarios where p-value is not really going to make much of a value, right? Um, right. Yeah. So what we are going to look into today is something which is a very common problem, right? Which is a very common problem. Let me just explain that first of all. Let me just get some cells over here and let me just try to explain it using a pen and paper. So what we were trying to do, let's say, example given that we were trying to in this case predict, right? We were trying to estimate the approximate value of sales quantity, right? So that becomes our y-axis. If I draw the x and y, right, then my y-axis becomes the, let's say, sales. Okay, so this is the sales quantity which becomes my y-axis, right? So I can just select this and move it over here. Yeah, and the x-axis, let's say, in our case, is the TV advertisement, right? So this is one variable where we have seen there is a very strong positive correlationship, right? So the more we spend on TV advertisement is a good amount of sale that we can expect out of it, right? So we have already seen this. Now, when we are joining multiple um, variables, then what is happening is, let's say this is my second x. Sorry, this is my second x, and my second x is, let's say, my second x is, let's say, radio. Okay, so in this case my second x was radio ad. So what essentially is happening is, in this case I'm creating a plane, right? Sorry, this is not giving me the right diagram. Maybe this one will. Yeah, so I'm essentially creating a plane which is something like this or something like this. Okay, so this is a 3D plane, right? And this 3D plane is helping me, or maybe I can change the color. In that case, that will be better. Yeah. So this is the plane which is giving me the regression or the relationship between these two variables. The variable which is over here, which is my radio ad, and the variable which is my TV ad, along with my sales ad. Now, we, as part of the exploratory data analysis, have looked into what is the relationship between, let's say, radio and sales. We looked into what is the relationship between TV and sales. But seldom we forget something, because the moment we are given a question, right, that I need to figure out what is the quantity of sales, I start looking at, or for that matter, anyone will start looking at the fact that, okay, let's say we have columns C1, C2, and C3. These are my independent variables. And then I have a target T1, which is my dependent variables. In this case, sales becomes my target, right? In this example, sales is my target, and C1 may be this one, and C2 may be radio, and C3 was the newspaper ad, right? So newspaper ad was C3, right? So the moment we get values like this, what we try and do in any kind of analysis is that we try to, let's say, let me change the color. We try to map the relationship between C1 and T1, C2 and T1, and C3 and T1, right? And we try to find out the correlation matrix, Pearson correlation coefficient, and so on. And we try to understand which of these variables, let's say C1 in our case, obviously, is having the most correlation with my target variable. And hence I say that clearly C1 is that one factor which is deciding what is going to be the quantity of sales, right? Now that's a good thing to do. I'm not saying that we have done anything wrong, but then there is something that we have missed, and that we have missed because of our nature. It is human nature to jump onto results as quickly as possible so that we can conclude as quickly as possible, and then we can do more, right, with the results. What we have not looked into right? What we have not looked into is what is the interrelationship between C1, C2, and C3. This is a very big question. Okay, what is the interrelationship between C1, C2, and C3? Clearly, when we plotted sales and TV, so it was something like this, right? It was something like this. There was a linear relationship between sales and the amount I spend on TV ads, right? What if, right? What if I look into, just another hypothetical example. Let's say I look into TV ads. Okay, I look into TV ads, and I also look into the investments I do in the radio ads, right? Right, and I see that there is a relationship between this data and this data, which is something like this. So it means that irrespective of how much I invest in radio ads, the TV ads value remain the same. So there is no such interdependency, right? There's no such interrelationship between the feature variables or the independent variables itself. I consider them as independent variables. That is the reason why I am assuming that they're independent of each other, right? But what if I do a control? What if I let the line be like that? What if there is a relationship like this? Or what if there is a relationship like this? Right? In this case, what is going to happen is, in this case, what I'm trying to convey is, if there is a positive, in this case, there is a positive relationship, or in this case, there is a negative relationship. If there is a positive or a negative relationship, how much slight that relationship might be between the independent variables, then my core assumption, right? My core assumption that the value of television ad investments and the value of radio ad investments are independent variables itself is wrong, right? Itself is wrong, right? What I mean by that is, let's say you have a very simplistic mathematical equation, x plus y, okay, plus some value, let's say 2, okay, is equal to 4. Okay, you have some kind of a mathematical situation which is explained by this formula. What I can clearly find, or what I can clearly see from this formula is that, okay, I can clearly see x is nothing but, if I take 2 on this side, then 4 minus 2 is 2. And then I take y on this side as well, on the right hand side of the equality sign, and this becomes 2 minus y. So clearly, in this case, if I want to figure out the value of x, I can simply figure out the value of y, right? And I can impute the value over here, right? Subtract that value from 2, I'll get the value of x. What if I tell you, okay, what if I tell you that this y is not y, this is x2. Okay, if I replace x with x1 and y with x2, in this case also, then I will replace y with x2. Okay, then x1 becomes 2 minus x2, right? The point I'm trying to convey over here is, if x1 and x2 are considered to be independent variables like c1, c2, and c3, and then I find there is some kind of a relationship where I can actually decipher one value basis the other value, then my core assumption is wrong. This clearly means that I have an interdependency between the variables, right? This problem of interdependency, and give me 1 minute, let me just check the last number I've used. Let me just check the last number I have used. Where is the last number? 9. Okay, so I'm going to use 10. Okay, this problem is otherwise known as multi-collinearity. Okay, one common problem. Okay, and this problem has nothing to do with regression. Okay, this problem is one general common problem across any inferential analysis that we're trying to do, any machine learning we would do, anything. This applies to anything at all that we do when it comes to data science. One common problem in the field of data science, the field of data science or machine learning or deep learning or AI, right, or any other related fields, is the fact that our assumption, okay, of all our feature variables being independent of each other being proven wrong, being proven wrong can prove to be very fatal, okay, for the resulting analysis, right? This is really very bad, very bad scenario, and this scenario is called, okay, this scenario is called multi-collinearity. Okay, this scenario is called multi-collinearity. Okay, it's a very, very dangerous kind of a scenario, and let's try to understand what effect multicollinearity has and how I can get rid of multicollinearity, or how I can look into multicollinearity. So first of all, a quick code. Is there any multicollinearity between in our data set, right? As of now data set, because please remember, uh, currently we have added, right, in the advertising data, now we have added a series of numerical as well as the categorical variables, right? So I'm going to take the latest version or the latest status of my advertising data and try to plot and see if there is any relationship between the variables within each other. And clearly, a very easy thing to do is to do a pair plot, right? A very easy thing to do is to do a pair plot. So I just say advertising, right? And I'm going to say plt dot show. Okay. Now there can be one problem, because in my data set I also have the scale and then is large, and then this targeted geography and then the divisions. So they might show me some kind of an interrelationship, but let's try to ignore them when we do this. Now, if I try to find this, you see the diagram is looking something like this. Is a very, very big kind of a diagram. I see there is some relationship over here. What is this variable over here? It is sales. Then it is fine, right? It is fine. I mean, I don't see any problem over there. But what about this? This is also sales versus radio. What about this or this? Is there any relationship of growth or any relationship of decrease? Because this is sales. This field over here is sales. Am I able to see any relationship? In my case, it seems that there is a slight relationship over here, right? A slight relationship that I can see over here. Other than that, I do not see any relationship. What is this variable over here? Radio, right? You see there is a very, very small relationship between radio and newspaper. Okay, so what is happening is there is some kind of a line that I can draw. Although the variance is quite good, I mean, I will not be able to get a very good regression line out of it, right? But it's quite clear there is still a relationship. But if you look at the final variables that we have settled with, right? We have settled with, let's say, TV and radio, right? So TV and radio seems to be the most common or the most important factors in this analysis. So this is TV. So this axis is TV. Okay, and this axis, as we have found, is radio. So you see over here, there is a complete scatter of data, right? The scatter of data is everywhere. I mean, you cannot plot any pattern over here, right? It is so scattered that it is entirely, I mean, it is close to impossible for you to find a pattern, right? The same thing applies over here, right? This is like TV versus newspaper, I believe. Let me just confirm quickly what is going on over here. Yeah, I was right. So this is newspaper. This part is newspaper. Let me take my pen. This part is newspaper, right? So TV does not have any relationship, any kind of relationship, right? It might be a relationship like this. It might be a relationship like this. It might be a relationship like this. It can be any kind of relationship. It may well even be a relationship like this, right? Or a relationship like this. There is no such relatable things that I see with respect to TV between the radio and TV between newspaper, which is a very good news, right? But if you look at this section, look at this section, let me just come down over here again. There is some relationship here. Okay, so what is this? What is this here? This axis over here, this axis that I see, I mean, my x-axis is actually radio ads, and my y-axis is my newspaper ad. So there is some kind of a positive relationship. I cannot say it is very strong, but there is something. I mean, I can plot. I can still try to plot a regression line. I can give this data. I can give this data to the stats model, and stats model will be able to figure it out. Okay, you can actually do that. You can actually create a stats model where n is a function, or this n or the newspaper ad is actually a function of radio, and it is going to return you a regression line, right? And maybe the significance of the regression line is also going to be quite good, although there is a lot of scattered here, right? So this is one very important thing that we need to know. Why is this something that we need to know? Why am I talking about multicollinearity? Is because if you have multicollinearity, you have a basic problem. Okay, you have a basic problem. The coefficient, okay, let's get back to basics. The coefficients of any linear regression or any regression model, for example, represent the extent of change in y, okay, or the target variable, when a certain value of x, right, a certain value of x, let that be only one x in case of simple linear regression, or it can be x1, x2, x3 until xn in case of multiple linear regression, is changed. So what I mean by that is, if anything in that values of x1 to xn is changed, okay, then there is a certain extent of change in y. So that is the relationship we are trying to figure out. That's the pattern which we are trying to find out, right? But if x1 and x2, for example, are dependent with each other, then that, I mean, my assumption that they are independent variables is wrong, right? So x1 and x2 are actually dependent. Then we are changing one variable, keeping others constant. That assumption itself gets wrong, and hence the model tries to do something, or my output, my analysis tries to do something that we need to define over here. It's a very important concept related to this, right? And it tries to remember everything. It tries to remember everything. It's like you are going for an exam and you have two guidebooks, and both of the guidebooks are giving you close answers to all the questions, right? You have two guidebooks that you are following, and both of the guidebooks are actually, right, are actually giving you very, very close answers, right? So you take any questions that you believe or that you feel has come in the last 10 years, right? And then you want to find the answers. Both the guidebooks, book one, book two, are giving you almost the close answer. Then is there any point? Is there any point keeping both books? The point is no, right? It is not adding any value. Having one book in this case is going to create a lot of less confusion as opposed to the other, right? It also results, this multicollinearity problem also results into a problem known as dummy variable trap. Okay, dummy variable trap is something which we reduced. If you remember, in the last class we had three classes of a categorical variable. We took only two, right? We took the degrees of freedom concept. We took only two variables and we mapped them with values, right? In that way we did the one hot encoding, right? We took only two, we mapped all of them, then we got rid of one. Why? Because same principle as the degree of freedom. If I have three unknowns and three equations, I need to solve only two to get the output for three. X, Y, Z, three unknowns, three equations using X, Y, and Z. I solve the first two, I get the values of X and Y. I simply impute that in the third equation, I can solve all the three at the same place. So I don't need the third equation. The third equation is going to create some problems. Okay, even the better way to identify this is to do this. Let's check the correlation, okay, or the correlation between my features. Okay, so what I do, I simply do my advertising dot core, right? I get the correlation, right? And I say SNS heat map, and I simply do it over here, and I say plt dot show, and it gives me the plot. So let me just do this plt dot fig size, sorry, fig size is equal to 12, 12, right? I believe this is going to be better. Yeah. So if I ignore sales, okay, sales is this column. So it is 1, 2, 3, 4. The fourth column is sales. Okay, you see over here, it is sales. Now, if I look only at TV, is there any strong relationship? Strong relationship is either given by a very dark color or a very light color. Okay, obviously TV is interrelated with TV. That is quite obvious. But look at this. Targeted geography R1 has a good color relationship. It's not that bad, but it can be considered. I mean, it's not really that bad. I mean, it's like in the middle portion. It's not really white. Okay, TV has a good relationship with sales. That's really good. But look at this pink portion. And this pink portion is that really good? It's okay. It's not bad. But then look at the radio. right? If you look at the radio and look at this section, right? The radio has good relationship with sales, but in the same fashion, the radio has good relationship with newspaper. So what I mean by this is I have three variables. Let's say TV. If I look at the original data set I got, I have TV, I have radio, and I have newspaper. Radio and newspaper seems to be interrelated with each other. So each one of them are answering the same question in the same way, in the same text, in the same method, right? So until and unless I get rid of one, it's really going to be a problem for me, because now the answer is always going to tend towards the right answer, which I don't want. I don't want any bias in my model. I do not want anybody forcing me to believe that there is a right answer to the problem. Why? Because this is not the exercise where you are already given answers to everything. Then you should not be doing the estimation. You're doing the estimation because you have some answers, you have some historical data. Using that historical data, you are trying to find what may happen or what you may want to estimate in the future data set. Right? So one dragging the other is a very common problem. So R is dragging N will be dragging R. And that's the reason why I need to get rid of one. Now, how do you get rid of that one? It's a very, very important question. Please sit down, okay, and try and understand, okay, spend a lot of time on this problem and try to figure out, do you have control on TV ads as opposed to radio ads as opposed to newspaper ads, or for your specific kind of product, okay, for your specific kind of product, which one is of primary importance? Obviously TV is good, radio is really good, newspapers are always good, but TV is quite something that everybody is doing, so this is good. I'm not saying TV is good, but can you really ignore the effect of radio or the effect of newspaper? Which one out of these two is such a business parameter, or such a parameter, such an aspect of the advertising side of your business that you can clearly ignore? Right? This is a business decision. This is not a decision that we can take statistically. We cannot look at a number and take this decision. We cannot look at a correlation coefficient and take this decision. We have to sit down and we have to think. And then the answer is going to dictate us. Let's go ahead. Let's go ahead and keep TV and the radio. Right? Out of these two, I'm going to keep only one. Right? So this is one way of handling multicollinearity. This is way number one. Okay. Way number two, very, very straightforward. I said there is no statistical way, but we are here to apply the basics of statistics only. So let's not diminish the value of that sign. So what we are going to do, I'm again going to go back to my basics. I take T, which is TV. I take R, which is radio. I take N, which is newspaper. I know the model is trying to estimate the value for sales. So I try to take combinations. I take a combination which is this. I take a combination which is this. Oh, no, sorry. Extremely sorry. I take a combination with TV and radio, and I take a combination with TV and newspaper. I create a model with this combination as opposed to sales. I create a model with this combination as opposed to sales. Right? So let's say this is combination one. Combination one refers to radio and TV, and combination two refers to TV and newspaper. I try to find out which one is a better model. I scale the data. I divide the data into training and testing sets. I test it thoroughly. I look at the R squared values. I look at adjusted R squared values. I try to minimize as much as sampling error or as much as external error as possible. Then I come to a conclusion. Okay, using C1, I am getting a model M1, and using C2, I'm getting a model M2. If M1 is better than M2, then I will say that I'm going to use TV and radio for my final modeling. Right? This is close to a statistical approach. I'll not say this is a really statistical approach. It's like an iterative approach. So you have tried out and then you have come to a conclusion. But the problem is, in our case, we are lucky. We have taken a toy example, a test example, and here we have only 3 independent variables. Imagine a real life business scenario where you actually have 10, 15, 20 independent variables. Is this really doable? if you're going to analyze your data, which is in GBs and GBs, and then you're going to model your data based on the combinations. Now imagine, I mean, how many combinations can it going to result into? Innumerous combinations will be there, innumerous. How are you going to tackle that situation? Is there any method by means of which we can tackle the situation? The answer is yes. Okay, there are certain ways, right? There are certain ways in which we can actually look into this. Okay, now give me 1 minute. Okay, so how to remedy, right? I mean, remedies of multicollinearity. Okay, let's write this. Have I closed this or what? Have I? No. It's there, right? Yeah. So remedies of multicollinearity. Remedies of multicollinearity problem are, first of all, you will not like this answer, but this is actually a good answer, right? If the relationship, if the interrelationship between the variables is not really that big, right? If the correlation is not really that extreme, forget it. Ignore if the correlation is not really that big, right? Clearly, you can ignore it. You can ignore if the correlation is not that big. I mean, it is big, but it is not that big. Let's say the correlation is only plus 0.3, okay, between newspaper and radio. If that is the case, then I don't think I need to take care of that. I mean, let's look at the data. So it's like advertising.com. Again, I'm going to look at the data. Let's look at newspaper versus radio. Look at this, 0.35. Is that really so high? I don't think so. I mean, if you look at just one side of the data, this is one value. These two are values. These two are values. This is a very good value. Okay, so sales and radio has a good value. This is okay. You can ignore its portion. Look at this. This is not so positive, not so negative. I mean, it's not really that big. There is a positive correlation between newspaper and radio, and yes, you can take a decision, but it is really not that big. Uh, right? So in this case, we can choose to for the multicollinearity problem because it is not causing a problem for us, right? So that's the remedy number one. You can ignore if the correlation is really not big. But if you believe there is a correlation, it is entirely up to you. If you believe there is a correlation and that is big enough for you to consider, then you may want to get rid of that. Okay, how do you get rid of that? Apply the same method as dummy variable problem, right? We applied a solution or a dummy variable trap, I'll say, right? We applied a solution for a dummy variable trap when we were doing one hot encoding. Okay, what did we do? We had 3 columns. We had 3 classes in one categorical variable. Hence, we created 3 columns. We dropped one, right? We randomly dropped one, right? By using the relevant business value. So this is the difference you should have in your analysis, right? So this is the difference you should have in your analysis. Okay, or third, okay, combine the correlated variables, right? Combine the correlated variables. Okay, maybe in this example that we have taken, it may not be practically possible to combine them. TV and radio are two different entities. They operate in a very different kind of a business model. So we won't be able to combine the advertisements efforts that my organization has with respect to, let's say, radio and the newspaper. I'm sorry. So radio and newspaper being completely two different areas in which they operate by themselves. It may not be very easy for me to correlate them or to conjoin them. But let's say if there is a data set where you have age and years of experience, right? You have age and you have years of experience in some data set, and these two are intercorrelated with each other, right? Can you create or can you get rid of this problem, right? There is one way, as per this third point, combine the correlated variable and create a new one, I can say. So create a new one, it means in this example, age and years of experience are interrelated. So I create a new variable called seniority, right? I create a mathematical function, okay, basis my understanding of age and years of experience. The combination of these two is creating a third variable, which is the seniority score. I give a seniority score to a person within the range of 0 to 10, within the range of 1 to 10, or a basis how old they are and how much years of experience they have in, let's say, IT, right? Then I can get rid of both. I get rid of both the columns age and the years of experience, and I only create my model using the seniority variable, right? Then my problem is solved, right? In this case, I'm completely ignoring both and taking only one. So I'm diminishing the effect of multicollinearity, but this is not always possible. I mean, if you look at the example we are talking about right now, it is not really possible over here, right? Or fourth, something which we are talking about from time to time, but we are not doing anything about it. At a later stage, we will look into it. Yeah, so don't worry. PCA, principal component analysis. We can do principal component analysis and try to find out the components or the features which are the most relevant for the model, which explains most of the variance in the data, and that we can do. But as of now, because we are not going into PCA, because PCA falls under unsupervised learning technique. Unsupervised learning is something which we don't know, right? We have not done unsupervised learning. We have only looked into supervised learning examples. We have looked into regression examples right now. We have not even completed that. Regression is where we already got the answer or the right answers to the historical problems. And that is why it's a supervised learning problem. Hence, we are not going to look into PCA. Let's find another easy way. Okay, is there any mathematical way? Okay, is there any mathematical way to do this? Okay, the answer is yes. The answer is actually yes. One useful mathematical, okay, method of taking care of multicollinearity, MCA, right? Multicollinearity problem, okay, is to use the point #2, okay, the point number 2, okay, is one, right? This one I'm going to use using some mathematical background added added onto the business background, right? So what I mean by that is, I know I have to take a decision basis my business background only, but why not improve my business knowledge based decision making with some math? To do this, I'm going to introduce a new term. To do this, we can make use of VIF, otherwise known as variance inflation factor. Okay, variance inflation factor, which is nothing but the regression. Okay, it is actually a regression. Okay, it is a regression of one x variable or one independent variable against the other x variables, okay, which is mathematically given as a formula 1 minus or 1 by 1 divided by 1 minus r squared, right? If I look at 1 divided by 1 minus r square, that division is done to penalize, right? The VIF factor is what I get. So variance inflation factor is what I get. Thumb rule, right? If VIF is greater than or equal to 10, okay, if VIF is greater than or equal to 10, it shows extreme correlation. It shows extreme correlation between the variables, and then we can get rid of the features from the descending order of VIF. right? So what I mean by that is, let's say I have found out the variance inflation factor of all the variables, and then I find that there is one combination of this variable which is creating the most variance, or they are interrelated the most. I get rid of that one variable. So there is already a very beautiful library which is provided by scikit-learn. So let me just save this first, and let's look into sklearn VIF. Okay, should be variance inflation factor. No, sklearn does not have. Okay, it should be there. Let me just check if it is there. Let's try to find out what it is doing. Let's try to find out. Let's try to find out. Yeah, stats model, outlier influence, variance inflation factor, right? This post we can refer, and we can try to find out what is the variance inflation factor. There is already all the functions, it seems, which are already created, right? So variant SMF it is doing. It VIF, there is a function which these guys are using. Sklearn and scikit-learn. Okay, yeah, yeah. Here clearly they are calculating the VIF, right? Right. So they are creating the VIF over here. That's a really good thing to do, and this is what, yeah, variance inflation factor is wrong. There is some bug which was raised back in 2015. I'm sure this is already resolved. So stats models has the variance inflation factor. So this is one way in which we can implement, or otherwise we can actually calculate it. As you see over here, so what it is doing within the data itself, it is fitting the model first. It is getting the R squared, and then it is calculating the VIF for each and every variable. If you look at the output, this is what the output it is getting. Okay, so for each and every factor, each and every feature, it is getting the VIF. So if this VIF example given, this is 3, we cannot get rid of any features from this. Okay, you see the features are this: alcohol, speeding, no previous, not distracted, and so on, right? But if you look at these values are really less than 10. Okay, I would in that case go with my first point, ignore, right? I'll ignore them, right? Let's look into it by code in the next class. Yeah, let me stop the sharing. We are going to continue by the next class. Yeah, thank you so much. Thank you so much, friends.
Thank you.
Thank you.